Learning outcomes. After studying this module, you shall be able to know what is dye, what is the composition of dye, what are the various types of dye, and what are the methods for dye analysis. Introduction. An important component of a fiber is its color. That can be an important clue for forensic scientists. Color present in fiber can be natural or imparted by use of dye. Chromatography is the approach available for forensic scientists. Chromatographic methods require the removal of the dye from fiber followed by its examination. Forensic analysis of dyes in fibers can be performed by thin layer chromatography, that is TLC, which is the most broadly used chromatographic technique. Instrumental methods of chromatographic analysis of dye consist of HPLC, that is high performance liquid chromatography, and CE, that is capillary electrophoresis. Now try to understand the dye. Dye can be simply defined as a natural or synthetic substance used to fasten a color or modify the color of something. Or it can also be defined as the different types of coloring particle varying in chemical composition and which are used for coloring fabrics. In forensic casework, dyes hold an important value in detection and evaluation of fibers. Next is the composition of dye. Certain dyes go through ketoenol type of tautomerism. This sort of tautomeric rearrangement results in an increase in formation and conjugation of a new chromatophore, thereby resulting in development of color. Such types of dyes are widely used in textiles. Some of the most common types are crystal violet, lactones, and furans. Now let us learn about types of dyes. Dye are complex, unsaturated aromatic compounds with satisfying individuality like intense color, solubility, substantiveness, and strong hold. It can be of various types like acid dyes, natural dyes, basic dyes, direct dyes, sulfur dyes, synthetic dyes, pigment dyes, wet dyes, reactive dyes, macromolecule dyes, metallized dyes, dispersed dyes, developed dyes, azo dyes, aniline dyes, mordant dyes. Next, moving on to the brief introduction of various types of dyes. First is acid dyes. These are the main class of dyes. The acidic component of the salt imparts color to the acid dyes. Acid dyes are combination of basic dyes of sulfuric acid or nitric acid. Acid dyes are generally used as linen or cotton. They are also widely used on nylon when high wash fastness is required. Acid dyes are typically soluble in water and possesses affinity for atmospheric fibers while lacking direct dyes affinity for cellulose fibers. When dyeing, ionic bonding with the fiber cationic sites accounts for fixation of colored anions in the dyed material. Acids are added to dyeing baths to increase the number of protonated amino group in fibers. Acid dyes are generally divided into three classes which depend on the fastness requirement, that is the level dyeing properties and economy. The class overlap and generally dependent on type of fiber to be colored as well as process used. Acid dyes affix to the fibers by hydrogen bonding, van der Waals force and ionic bonding. They are normally sold as the sodium salt. Therefore, they are in solution anionic. Animal protein fiber and synthetic nylon fibers contains many cationic sites. Therefore, there is an attention of anionic dye molecule to a cationic site on the fiber. The strength of this bond is related to the tendency of the dye to remain dissolved in water over a fixation to the fiber. Now next is natural dyes. It is the most common method to apply color on fabric. Overprinting is the method where natural dyes are applied on colored fabrics. This is done by pressing the natural dye onto the fabric in a glue form to create the desired pattern. The dye is dispersed in mixture of a thickening agent and limited quantity of water for preparation of paste required for printing purpose. Next we have basic or cationic dyes. Cationic dyes are developed from the organic base. These bases are soluble in water and are frequently used to dye acrylic fibers. They are generally used with mordant, which is a chemical agent used to place dyes on fabrics by forming an insoluble compound with the dye. Cationic dyes are used for nylon, cotton, acetate, linen, polyester, mod acryls with mordant and acryl. Now next is synthetic dyes. The first synthetic dye is Movin was discovered by William Henry Perkin in 1856. Synthetic dyes classification are derived from their chemical composition and process of how they are applied during drying. The synthetic dyes can be named according to the chemical structure of their particular chromatophoric group. For example, diphenylamethane derivatives, triphenylamethane compounds, oxime compounds, xanthine compounds. Azo dyes are one of the most popular varieties of synthetic dyes. Today, it is being used up to 90% in the dyeing units as they are versatile and simple to synthesize. Most of the synthetic dyes, with a few exceptions, are aromatic organic compounds which can be divided into groups like non-ionic, that is oil soluble, cationic and anionic. Next is direct or substantive dyes. These dyes impart color to the fibers without the requirement of mordants. They are commonly used to dye cotton, nylon, wool, silk and rayon etc. And also these dyes are not very intense in color. The color of direct dyes are duller than those provided by fiber reactive dyes and the wash fastness is poor except anything dyed with them to bleed forever. The one advantage is that direct dyes may be more light fast, that is resistant to the fading in the light than the fiber reactive dyes. The direct dye classification in the color index system refers to the various planar, highly conjugated molecular structures that also contain one or more anionic sulfonate group. It is because of these sulfonate groups that the molecules are soluble in water. Though most direct dyes still can be obtained in powder form, it is increasingly popular to receive them as liquid concentrates. The advantage of concentrates is that they are easy to handle. The disadvantage is that the surfactants and co-solvents needed to keep the dye concentrates stable may interfere with deeply colored grades. Next is dispersed dyes. These dyes are present in the form of paste or powder that are dispersed in water and are generally insoluble in water. Dispersed dyes give color to the fibers, usually by getting dissolved in fibers. Such dyes were basically developed for dyeing of cellulose acetate, but now they are being used to impart colors to acrylic, cellulose triacetate and nylon fibers. Next class is of sulfur dyes. These dyes are usually not soluble, but by using sodium sulfite and caustic soda, sulfur dyes can be made soluble. For the purpose of dyeing, sulfur dyes are mixed with large amount of salt at high temperature so that the fibers takes up the required color. The desired shades of color are given to the fiber by exposing them to air or by using chemicals such that the fibers get oxidized after dyeing process is completed. Excess amount of dyes and chemicals are removed by washing. They are mostly used for cotton and linen. Next class is of pigmented dyes. Pigmented dyes are not dyes. They are used to impart color to the fabrics such as wool, cotton and other synthetic fibers because of their outstanding light fastness. These dyes are not fixed to fibers but are bound by resin onto the fabric. When dyeing completed, the fabrics are kept at high temperature. Next class is of mordant dyes. Mordant dyes are also known as chrome dyes, which are acidic in nature. Generally, sodium or potassium dichromate is used with mordant in dye bath. Wool gets a strong hold of color after being treated with mordant dyes when the dyeing is finished. Mordant dyes are less effective but still are used to color silk, linen, cotton, rayon and nylon. Next is wet dyes. Wet dyes are insoluble in water. By the help of reduction in basic medium, wet dyes are made soluble, which allows them to fix with the textile fiber. These dye in original is indigo in color. Wet dyes are good for coloring fibers of linen, cotton and rayon. Besides, these wet dyes are used in combination with mordant to impart color to fabrics. For example, nylon, acrylics, wool, mood acrylics and polyesters. Next category is of reactive dyes. These dyes, when reacted with the fiber molecules, lead to the formation of a chemical compound. Reactive dyes are alkalized after the application with a neutral or basic solution. Sometimes to create different shades, heat treatment is also done. For removal of any unfixed dye, after the dyeing process, the fabric is washed. These are mainly used for fabrics of cellulose simply, although now they are being used for acrylics, wools, nylon and silk. Next category is of macromolecular dyes. Macromolecular dyes are a group of inherently colored polymers, are useful for both polymers and dyes as well as with high color yield. These are also used in case of writing inks, for dyeing hair and for mass drying. Next is metallized dyes. Metallized dyes are group of dyes which carry metals in their molecular structure. For the application purposes, acid bath process is used. Metal complex dyes that are otherwise known as pre-metallized dyes shows great affinity towards protein fibers. Generally, it has been seen that the metal complex dyes are chromium or cobalt complexes. Among the popular metal complex dyes, a variety known as 1:2 metal complex dyes finds application for dyeing polyamide fibers. For dyeing wool, metal complex dyes are most favored. Next category is of developed dyes. Developed dyes are dyes which are formed by the help of developer. Substrate is first dyed in a neutral solution in a dye base, which is usually colorless. Then it is diazotized with sodium nitrate and an acid, and then treated with a solution of beta-naphtha, which is a developer. Now let us learn about the azo dyes. These dyes usually come under the category of synthetic dye classes. Azo pigment consists of colorless particles, typically earths or clays, colored using azo compound. Azo pigments are important in a variety of paints including artist paints. They have excellent coloring properties, again mainly in the yellow to red range, as well as good light fastness. The light fastness depends not only on the properties of organic azo compound but also on the way they are being absorbed on the pigment carrier. Next is aniline dye. Chemically, these dyes are obtained from aniline or from other derivatives of coal tar. The principal use of aniline in the dye industry is as a precursor to indigo, the blue of blue jeans. Varieties of other dyes are also available that includes like fluorescent dyes. These dyes are for application in sports good. Fuel dyes are used in fuels. Leather dyes, they are used for leathers. Inkjet dyes used in writing industry. Oxidation dyes used mainly for hair. Optical brighteners used primarily for textile fibers and papers. Now let us learn about dye analysis. Forensic analysis of dye is thus usually carried out to compare questioned sample with controls to identify a particular dye. Two issues faced by forensic analysts while analyzing fiber dyes are: first, the difficulty with the wide variety of dyes and fibers and potential combinations. Second, the destructive nature of chromatographic analysis due to the extraction of the dye from the fiber. First is the dye extraction. Dye extraction is the first and the basic step in the analytical process of dye and fibers. Varieties of solvent have been introduced for a number of extraction schemes. These extraction schemes vary but have basically the same aim, which not only extract the dye but also can be classified in TLC, was normally applied for the purpose of identification and separation process. Extraction process. Single fiber is located in a glass tube which is 2.5 cm into 1.5 mm ID and sealed at one end. After the solvent is added, this should be around 10 microliter, as it is sufficient to immerse the fiber completely. The tube is sealed under heat for the required temperature and time before incubation in an oven. Control samples are utilized in order to establish dye class, and best extraction procedure is applied prior to the analysis of recovered fibers. Next is dye analysis. First, thin layer chromatography. Since 25 years in forensic science, TLC, that is thin layer chromatography, has been used for comparison of control and question fibers. The most important advantage of this technique is its ease as contrasted to different chromatographic techniques. Like, the analysis involves first the selection of suitable stationary phase, selection of mobile phase, development, and the visualization and detection. For the analysis of dye fiber, aluminum backed silica plate is recommended. Before using the plate, it's been suggested that these silica plates are stored in dissectors or heated. for making sure that any water present must be driven off, as this will vary the activity of the silica stationary phase. For dye analysis, TLC is one of the simplest methods for separation. For its analysis, glass capillary or micropipette is used for spotting of approximately 2 mm in diameter, usually about 1 cm from the bottom edge of the plate. The solvent is needed to apply the sample should be capable of wetting the stationary phase, and it is supposed to be volatile also, such that it is moved off before to the development of plate. It is suggested that question sample, control sample and standard dye are run at the same time. As the plate is completely dry, it is kept in a pool of eluate containing a covered chamber. This can be as simple as a beaker covered with a petri dish. After the plate is kept covered in the chamber, the level of eluent should be lesser than the spots applied on the plates. Capillary action will take place as the eluent will travel up to the plate. As the process will complete, the separation of the component can be observed. The eluent used for TLC or fiber dyes will depend on the class of dye being analyzed. Analysis of the developed TLC plate is carried out by comparing the band position and the colors of the question and control fiber extracts. This is done under the normal laboratory lighting or the use of ultraviolet light. Finally, the RF values can be calculated. Now next step is dye analysis by high performance liquid chromatography, that is HPLC. This technique was introduced during the period of 1960. In forensic science, this technique has been widely applied as an analytical technique for qualitative and quantitative analysis of drug and metaboloids, organic and inorganic explosives, marker dyes and inks. There are various advantages of HPLC over TLC. For example, better resolution of dyes, quantitization and consistent retention times of separated components. The essential part of HPLC consists of pump, an ejector, column, a detector and a recorder or a data system. The separation takes place in the main part of the system, that is the column. Pathway in HPLC, that is solvent, pressure gauge, pump injector, system column, detector, waste container, recorder. The stationary phase normally consists of porous particles of micrometer size. The mobile phase moves through the column by a pump. The chromatographic process begins by introducing the sample into the system manually or automatically before the separation starts by using a variety of injection devices. Early constituent is eluted from the column in the form of narrow band or peaks in the recorder. Separation resulted in recorded as a graph electronically using a computer, which is referred to as a chromatograph. HPLC is tremendously a great separation technique which is used extensively as an analytical process in various areas of forensic. HPLC has an advantage for analyzing extremely small samples of material. Combination of HPLC joined with mass spectrometry has been applied in forensic for dye analysis. Now next is capillary electrophoresis. Capillary electrophoresis is a family of electrokinetic separation methods performed in sub-millimeter capillaries and in micro and nanofluidic channels. Very often, capillary electrophoresis refers to capillary zone electrophoresis, that is also called as CZE. But other electrophoretic techniques including capillary gel electrophoresis, that is CGE, capillary isoelectric focusing, that is CIEF, capillary isotopophoresis, and mesoelectrokinetic chromatography, that is also called to be MEKC, belong also to this class of method. In CE method, analytes migrate through the electrolyte solution under the influence of an electric field. Analytes can be separated according to ionic mobility. Additionally, they may be concentrated by means of gradient in conductivity and pH. Its forensic application was first given by Weinberg and Leray. Capillary electrophoresis is so attractive for forensic analysis for its minimal sample preparation, low reagent use, waste production, and its separation power, simultaneously followed by a quick analysis. Capillary electrophoresis describes a cluster of techniques where separation of components occurs in narrow bore capillary of chemical mixture under an electric field. Separation and capillary electrophoresis are based upon the migration of charged particle through a fused silica capillary filled with background electrolyte. Detection is usually by ultraviolet visible absorbance spectrophotometry, resulting in graph, which is similar to the chromatographic separation and also known as chromatographogram. Lastly, moving on to the summary of all that we have learned in this module. Dye can be simply defined as a natural or synthetic substance used to fasten a color or modify the color of something. There are many types of dye like acid dye, natural dyes, basic, that is cationic dyes, direct substantive dyes, dispersed dyes, sulfur dyes, pigment dyes, etc. Dye analysis can be performed by variety of methods like TLC, HPLC, and capillary electrophoresis after extraction of dye from fiber. Extraction of dye fiber is done by solvent and detection by TLC. Extracted dye is identified accurately by high performance liquid chromatography. Thank you.